in the previous classes that for any motor drives, we basically have three aspects to look into. One thing is your power electronics, which includes your motor, and we have the load. The second aspect, we need to understand what is the load that we are going to operate with our motor. And the third and very important aspect is controller. So first aspect, load part, we have done quickly in our first class, and in the next class we were going into the basics of what controller does and what are the requirements of a controller and why do we need feedback based control, particularly the unity feedback or any such control. So we have seen what are the advantages. You may go back to the lecture and refresh that. So today we will learn how to design the controller for any system. Let us say we are taking the example of the separately excited DC motor. And this is operating a random load. So how to design the controller for this? This is what specifically we are looking in this class. And if time permits, we will move towards the power electronics design. So as and when we get the requirement of anything in our system, we will discuss that. There won't be any abrupt discussion on any other topic. So what we have understood that our separately excited DC motor is basically having two parts. One is electrical. So where we have equation like if your applied voltage or armature voltage is V, so the current, armature current is having this kind of dynamics. This is your electrical part. And we have mechanical part where we have seen the electromagnetic torque, which is basically equal to some constant times, let's say I call the constant C. K is going to come many times. So some C times of your armature current, and which is going to be responsible for balancing the load torque plus the other mechanical dynamics along with some frictional component. Now this is what our system is, and we have seen that with some feedback control, we are trying to have a speed control of the DC motor. So basically, if you draw the complete system block diagram, what you will have is basically there is a voltage input, let us say VA. So here you have the EB getting subtracted, and then you have the electrical plant coming over here. So I am dropping some of the subscripts so that is understood. And then you have the current generated from this, which is going through a gain of C to generate the torque. And then you have the load torque getting subtracted over here. And this again goes through the mechanical dynamics. And this is generating your omega. Now this is the system what we are having. So essentially your EB is generated from omega, which is again a constant times omega. These two constants are same, the torque constant and speed constant or back EMF constant. These two are same. And we have these two quantities which can be measured. Now this system we are trying to have a controller. Now here we have to understand this VA is generated through a power converter. Power converter works on basis of what input signal is given to that, and whatever reference signal we give to that, gain times of that reference input is our output. So our VA is nothing but some K times of VA reference. This is the model for the power converter. DC-DC power converter what we are having over here. This we will see how this gain is coming up and how we design this power converter, that and all will come in the subsequent classes. But here we more focus on the controller design. Now this reference for the converter is basically generated from a controller which is a current controller. So we have talked about the cascaded control system, so which is what we are trying to see over here. Now in the cascaded control we have the inner loop where the current control is coming up. It has a current reference and the current feedback. This current feedback is essentially your this quantity IA. It may or may not have a filter. Now this current reference is basically generated from another controller which is your speed controller. So other people may please mute their mics. Now this speed controller is having a reference speed given by us, and then the feedback which is basically measured speed, but it comes through a speed filter because it's an external quantity, so we will have a lot of noises that we need to filter out. It could be a low pass filter which we will see, first order filter. Now this is the structure what we have discussed in the last class. Here we have basically two control loops. One is the inner control loop. If I draw the dotted line, up to this is our inner control loop. And we have seen that for any cascaded control, the inner control loop must settle very, very fast or very, very quickly compared to the outer control loop. So which means the bandwidth for the inner control loop should be very, very greater than the outer control loop. So what is very, very greater than, which means that it is at least 10 times the outer control loop. So this is the basic concept which we'll be following. Now let us see how to design this particular inner control loop which is there for the current control. Now what we have basically the system, if we see over here, we have the quantity VA. It's having the back EMF getting subtracted and the plant, and that is generating our armature current. Now we see that in this equation, except EB, this other part of the equation is a first order linear system. So we have an input and we have an output, but this part EB comes from another external quantity called omega. So we have to compensate for this EB. So compensation, as I told in the last class, is done in a feed forward manner. So what do I mean by feed forward compensation? That the moment this signal is generated for the power converter, there we add this EB. So let us say our controller having a reference input I, having a feedback I feedback, is having this controller is generating this VA reference. So here itself we add this EB, and this will basically, after passing through the KA, will basically take care of what is getting subtracted further from the generated voltage. Of course, because there is a gain coming up over here, so this cannot be EB directly, but it has to be divided by the gain, so that it also becomes a signal. So 1 by K times EB. So now what we are doing, we are simply compensating for whatever EB is going to come into the system before it comes. So in the controller part itself, this is all controller part. Before you apply the signal to the controller, I mean the power converter, this is all your controller. Let us say the previous quantity is VA1. So this is our actual reference for the power converter VA star, where VA1 star is nothing but your VA star minus EB by K. Now, this is the control loop which we are trying to design. So we have taken care of the non-linearity which was there in the system. Now what we have is a perfectly linear system. It's a first order system we have seen. And what we have, input, feedback, and then the plant controller and some of the disturbances coming, which is because of the EB addition or subtraction. So while designing the controller, we may ignore these disturbances. These we need not consider for the design. So any disturbance, we have seen that if our input is 0, the disturbance coming to the system will be automatically attenuated by our controller. So the remaining control loop looks like this. Now here, what is the controller that we are going to use? So for practical applications, I have told in the previous class that we use a PI controller where it has two components, KP plus KI by S. So our objective is to design these KP and KI parameters, which means to come up with an equation or formula for this KP and KI, which is derived on basis of certain performance parameters. Now, what are these performance parameters? Since it is a first order system, it is perfectly stable. There is no issue of instability. So then what to do? When it is perfectly stable, then what do we want? So three things we have discussed in the previous class. What we want, because this has a slow dynamics. So our time constant L by R is of the order of few milliseconds. It may be few tenths of millisecond. So this we want to make faster. So that let's say our control loop settles within 1 millisecond. So it is a much faster system compared to let's say 20 millisecond or 30 millisecond of time constant. So this is first requirement. What is the second requirement? That the dependency on the parameters, which mean if there is some parameter variation, so it should be able to take care of that. So take care of any parameter variation, and if there is any disturbance coming, you should be able to reject that. So these two things, which are parameter variation and disturbance, these are automatically taken care by any feedback control system. The only thing we have to ensure now is we make our control loop faster, which means we have a good bandwidth for our system. Now, what is the meaning of bandwidth? If I tell in terms of step response of any system, so you all must have read in your control courses that if there is unity input given to the system and there are two systems, one is responding like this, which means taking lot of time to reach the input value, and another responding in a very shorter time, reaching the input value very quickly. So the bandwidth of this green system, let's say BW2, is greater than BW1. So it's having a much faster response time, which means the time constant for 2 will be lesser than time constant for 1. By the way, this is always true. The time constant into bandwidth is equal to 1, which means it is just reciprocal. So now this is what we are trying to design. Now our KPKI should be designed such that if this is the response of our original system, it should become like this, much faster system. Now how do we do that? So we have this block diagram. I will just go back to that. So if you note, there are 3 parts. Maybe for clarity, I will write it again. The control loop along with the KP and KI, what we have given for the PI controller. Then we have the power converter, and then we have our machine. So this is generating our reference current. So now if we write the open loop transfer function of this system, it is R plus SL, or if we reorganize this may be written as one factor, and then another factor could be written as Kp by Ki times of S, and this can be written in terms of time constant, where tau is nothing but L by R. So now we can see this is a first order system, not going to go unstable, so we need to take care of the pole which is little slower in response, or which is having a bigger time constant. So what we can do, we can cancel this slower pole with our controller 0. So we can have the facility that if we maintain Kp by Ki is equal to tau, so we will be able to have the pole 0 cancellation. So which means we will get rid of these 2 terms, and what we will be remaining is only this factor, which is again a first order system. Now, so far we have got one relation between Kp and Ki when we are cancelling our slowest pole, and now one more equation we need so that we can get the exact formulas or exact value for Kp and Ki. Now what we do, we write our closed loop gain from the open loop gain. So now this means what? Now we have some I star after the model reduction, how it looks. So this is our model, which after the pole 0 cancellation, this is how it looks like. So here the closed loop gain, which means if we have to write the expression for I by I star, that can be written as this. If you simplify, we will find that it can be written in this form. Now, this is what we are trying to achieve, which means a good bandwidth. So how do we decide what is the bandwidth? Let us say we go for the Bode plot, only the gain is sufficient to tell what will happen. So let's say this is your 20 log G. So for this system, we know that initially it is only this constant K, which is 1 coming over there. So our plot will start from the 0 dB line. This is 0 dB line. And the moment it reaches this value of corner frequency Ki, Ka by R, that is where it will have minus 20 dB per decade slope. Please refer to the previous class to understand how these things are coming up. We have seen how to plot the phase and gain in the Bode plots. Now, the actual plot will have a deviation of -3 dB near the corner frequency. This difference between the actual and asymptotic plot will be -3 dB. This is the definition of our bandwidth also. The frequency at which the deviation is -3 dB from the actual value, that defines our bandwidth, which means the quantity which we are looking at this point, which is Ki by R, this actually corresponds to our omega bandwidth. So let's say if we have F as our bandwidth frequency, so then this is the relation between the two quantities. Now we have a clear equation between the Ki and the other desired variables, which means the FBW, R and Ka. So in this, R is known, which is our machine parameter. Ka is known because our power converter is there. We will see what is Ka actually. But as of now, you assume that it is known for a given converter. Now, only thing unknown is FBW. Now, how to decide the bandwidth? So, any system, the thumb rule says that if we have switching frequency of converter given as FSW, then we can have our bandwidth 1/10 of that switching frequency. So let's say we are having a switching frequency of 1 kilohertz, then our bandwidth could be 100 hertz. So this is the thumb rule which we follow, and then if we follow that, we know the value of Ki, and then because we have the relation between Kp and Ki given by the first equation, Kp by Ki equal to tau, so we know what is the value of Kp in terms of Ki or in terms of the actual expression. So here tau is basically L by R. So now we have seen that how we design Kp and Ki, which means the parameters of the controller for the current control loop when we have plant given as this 1 by R plus SL, we have power converter K gain and FSW switching frequency, and we have a PI controller. So we know now how we can design these Kp and Ki parameters. So if you can plot these Bode diagrams or Bode plots in system in MATLAB you want to try, or you yourself want to try, you can compare that how this time constant 1 by RSL has changed to something much faster, which is the controller or control loop time constant, which is omega BW. So one part of design we have completed, which means whatever is there in the red block, that is complete. Now what we need to design is the controller for the speed loop, that is the outer control loop. Okay. Now here is the beauty of the cascaded control that we will see. So we have speed controller, generating the current reference, and then we had the comparison, then the current control loop, so I am ignoring some of the disturbances in the current control loop as those are not critical for designing. So this was our system to be designed. Now what we have done, we have designed the section which is encircled in the red. So what we have found, that our system which is encircled in red, that reduces to a current input, okay, maybe if you include the feedback also in this one. So which means in an equivalent manner, if we write that our I reference is given to this plant and it is generating our actual current. This is what essentially this red circle means. So we have reduced the plant to this and we have designed the K and Kp and Ki in such manner that it is generating the desired result, the desired current. Now this can also be written in a form what we have designed as the time constant or the bandwidth of the system. It can be written like this. So this complete red circle we can actually replace with only this part, the I reference going through a first order plant and generating the actual current. So if we replace that, our system reduces to speed reference, speed feedback, speed control, which is generating the reference for current, and then this plant. And then we have the current generated, which is going through the constant C generating the electromagnetic torque, and then we have the load torque which is generating the speed after the mechanical dynamics. So this is the beauty of our cascaded control, that we have gotten rid of lot of things which were falling inside the current control loop. Now we have only a first order system sitting there instead of that big loop. Now here few things. This filter, what we have as for rejecting the noises getting inserted in the output speed. So this filter is basically a first order low pass filter. Which basically can be written as this, where tau f is the time constant for the filter. And this is up to us what we want to decide as time constant. Let us say we say like the corner frequency for the filter is 10 Hertz, then our time constant will be 1 by 2 pi 10. So it is up to us. We are free to decide what frequency we want for the, or what time constant we want for our filter. Now the speed controller, again it could be a PI controller or PID controller if little more robustness is needed, but we are happy to take PI controller over here. So for differentiation I will use the subscript omega in the Kp and Ki terms. So this is our PI controller which we will use for the speed control loop. Now with these two quantities, if I redraw the block, how it will look like that our speed reference and the speed feedback, these are generating the error which is getting fed to this controller, and then we have the first order current control loop in this form, and then our mechanical systems. So I will ignore the load torque because that comes as disturbance. So here we have mechanical system coming out like this. So you can compare here. You have only the load torque coming in between. So that can be ignored for the controller design. And then we have this. And in the feedback path, we have another term added, tau f. So any practical system is done like this. If you go to industry and want to design something, any speed control loop, you must have these components available in your system. Now, if we write the open loop gain for this system, so there are so many components. So on contrary to what we have seen in the current control loop, here we have a lot of things coming over there. So for example, if I write the open loop gain, this is your controller, then you have your current loop, and then you have your mechanical system, and then you have your filter. So it gives almost a fifth order dynamics. So which is a complicated system to design and not similar to what we have seen for the current control, that you have a pole zero cancellation and then done. So here it needs little more involvement in terms of design. First thing, what we need to understand about this mechanical time constant, this is a pretty huge time constant. This J by B, what is coming over is maybe few tens of seconds or even up to a minute. So most of the time we ignore this B, which means we take that this time constant is infinity compared to the other time constants which we are dealing with. So it's only relative. So we can write this as C by Sj. So this B term we are ignoring because it's a very small number, and that is why it gives a huge time constant to the system. So let us ignore that. Ignoring means we are considering the worst value. If it is there, it will only help us if it is having any little higher value. So let us take the worst scenario when B is 0. Now what we have, 4 components we are having over here. Now compared to the mechanical time constant, these two time constants are pretty far. So what we can write, we can try to have a model reduction for this system. So is there a way in which these two terms can be clubbed, which is the filter and the current control loop coming up? So if we have a system like this, I will take this part first. Let us try to reduce this. So what it is going to give, that if you take the product as it is, it will have this expression. Now in this one, tau I value, we have seen that it corresponds to 100 Hertz. That means 2 pi 100. This is the value of tau I, and tau f is something 2 pi 10. So the order of this quantity and this quantity is something like, if this is, let's say, 1 millisecond, this is, let's say, 10 millisecond. So we have total the values of this coming of the order of 1e minus 3 and 1e minus 2. something like that. So which means the product of these two, tau I and tau f, is going to be of the order of 1e minus 5, which is a pretty small number. So then this term can be ignored. So the approximation for these two terms could be tau f. This sum we can write as another time constant, let's say tau 1, and so this double pole thing we have reduced to approximated to a first order system. So which is how we can have the model reduction for our mechanical system. Now if we see our mechanical system, what is remaining over there. So if I reorganize also a little bit so that we can see it clearly. So we have C by Sj, and then if you reorganize the controller part so that you can have clear pole and zero distinction. So I am dropping the subscript omega. Please remember that it is there for the speed control. And then this S tau 1, that is there. So this is our plant. Now if we look carefully, this is not similar to our current control loop that we cancel these two poles and zeros and then we have the design. No. Why? Because apart from this constant, what is there? C times of Ki by J, we have a double pole sitting at the origin. One by S square is basically indication of a double pole sitting at the origin. Which means that our phase of the system is already minus 180 degree at the origin itself. So in any case, we are not going to have any phase margin for the system at the gain crossover frequency, which implies that the system is inherently unstable. So whatever amount of pole zero cancellation you do, it is not going to help over here. So in other words, if we just plot the Bode diagrams and see the gain and phase plots, let's say this is our 0 dB line and this is our 0 degree phase line. So let's assume this is 180. So our plot is starting with 1 by S square, which means it has minus 40 dB per decade of slope in the beginning itself. So it's dropping steeply. And so our phase is also starting from 180 degree. So if you allow this phase, the gain to cross this gain crossover frequency with the same slope, then our phase is going to be minus 180 degree at the time of gain crossover frequency. So which means we have phase margin equal to 0 in this case. So this is what is the unstable system. Now we want to make this system stable. So we have few things at hand with which we can play. So this is where we go for another technique. Instead of pole zero cancellation, we go for symmetric optimum method. What symmetric optimum method says that, okay, you are having minus 40 dB of slope at the beginning, but at least when it is crossing the 0 dB line, that time if we can change the slope to minus 20 dB per decade, then we can have some phase margin over here. So our phase will start improving before the gain crossover frequency, and it will have some positive value when it crosses. So for symmetric optimum method, they say that if our gain crossover frequency omega n, let us say, is such that it is geometric mean of the zero and pole frequencies in the system, then we can have maximum phase margin. Whatever we target phase margin, that we can achieve. So where is the pole in our system? That is given by the current control loop. This is the pole omega p, or corresponding to this, and then this is our zero. So we have to locate our omega z, because omega p is fixed. So omega z we have to locate such that our omega n falls in this criteria. So other words, if I say omega n is nothing but omega z times of a, some factor, if let us say we take a, then our omega n is basically a times of omega z and 1 by a times of omega p. This is the definition of this geometric mean. So these three are in geometric progression, where the factor a can be determined on basis of how much phase margin we want. So now we have three unknowns to get over here. So we have kp omega, ki omega and a. If we know these three parameters, then our control design is done. Now coming back to our phase plot and the gain plot. So what will happen? Let us say we locate our omega z somewhere here. So what will happen? That up to this it will have minus 40 dB per decade slope, but at this omega z, the slope will change to minus 20 dB per decade. And it will continue. And let us say our omega p is quite far, so it will have the gain crossover frequency coming at minus 20 dB per decade. And then again, when our omega p is encountered, it will come back to the original slope, minus 40 dB per decade. So what we have achieved over here is that we are crossing this 0 dB line. This is the frequency I am calling as omega n at a slope of minus 20 dB per decade. Now what will happen to the phase? Certainly, because we have a 0 coming up over here, so there will be some improvement. So 1/10 of omega z, which is where our phase will start improving. That's what we have seen in the previous class, how to have these gain and phase plots. And 10 times of omega p, it will again come back to 180 degree. So how it will look like? So here it starts improving. This is where it will maximize, and then it will start falling again, and it will match this 180 degree at 10 times of omega p. So something like this. Now what will happen? Because the phase has improved from 0 degree to some phi, we have a positive phase margin. This is the phase, mind it. This is the phase margin, what we are getting. And since this is greater than 0 degree, so now we can say that our system is stable. So this is what the symmetric optimum method is, which will locate your 0 and pole such that you get a phase margin of greater than 0 value. So typical phase margin could be 45 degree, which we get, and then we can have a stable operation for the control loop. Now, the more important things, how do we calculate these values based on these conditions what we have derived? So there are three things. One equation we have got that our omega n is a times of omega z and 1 by a times of omega p. This is our first equation which we are having. The second equation, the phase at this point omega n, this is omega n, this is 180 minus phase margin. So phase of the system, open loop system, is minus 180 degree plus phase margin. This is our phase. This is the second equation. And the third equation is the gain, because it is a 0 dB line what it is crossing. So definitely the gain of the system, this 20 log something, is 0, which means the gain is equal to 1 at omega n. So these three conditions, if we solve, we have three unknowns, Kp, Ki and A. So these three can be solved. Now let us say at least one thing I will solve over here, and the other things then you may do as an exercise. So let's first take this phase. So phase of this open loop transfer function we can write as and let's say I write this Kp by Ki in form of omega z and the pole in form of omega p. So this is how it looks. So from the previous lecture we have seen how are we writing the phase of any general system. So that's what we will imply over here. So we will decouple these systems. Phase of this constant plus phase of 1 by s square plus phase of our 0 plus, because it's a pole, so we can write a negative sign over here. Otherwise we need to write in the inverse fashion. So now we can write like this. So we know the constant is having a 0 phase. So this is 0 plus this is double pole coming over here. So minus 180 degree straight away plus this is a first order 0. So that has a phase of tan inverse of S will basically become your omega n, at which we are calculating the phase. So omega n by omega z, and minus tan inverse of this omega n by omega p. So this is the first equation. Now phase, we have seen that it is minus 180 degree plus the phase margin. So here it becomes minus 180 degree plus tan inverse, and now we can insert the values from equation 1. So this factor becomes tan inverse of A minus tan inverse of 1 by A. So then this equation becomes simple. We have a very straightforward trigonometric equation to solve. So we have tan inverse of A minus tan inverse of 1 by A equal to the phase margin, whatever is desired. This phase margin is up to us, what we want to have. Let's say we want to have 45 degree. So then we can solve this. And from here we can have, because tan 45 degree is 1, so this is the final equation what you will have. Now if you solve, and because A is a positive quantity, a positive ratio, so we will go for the positive solution of this, and it will come something like this. Now we have solved one thing. So if we have this value of A, we can straight away tell what is our omega n. So that is omega p by A. Omega p is nothing but tau I, 1 by tau I. So we have omega n, and then we can tell that our omega z is A times, 1 by A times of omega n, which means if we insert this, it is 1 by A square times of tau I. So omega z, by the way, is Ki by Kp. That's what we have seen. So we have got another relation between these two quantities. Now the third one, which is the magnitude equal to 1, this I leave up to you as an exercise. You can solve, and then we can have the expressions for the KPKI, what we are going to put for our speed control loop. So Kp omega is function of few quantities, Ki omega is function of some quantities, which includes A as well. So this is what is giving you the design parameters for the speed controller. Now one thing to note over here, if you ask what is the bandwidth, so the open loop gain crossover frequency is typically called the bandwidth of the system. So this whatever value of omega n we are getting, that is basically our bandwidth for the speed control loop. So now we know what bandwidth we are designing. So when you have current control bandwidth FB omega as FSW by 10, so your FB omega I, let us say, for the current, now if bandwidth for the speed, let us say B omega omega, that will be FSW by 10 into 10. So it is 10 times slower than the current control loop. So while deciding the parameters A and phase margin and all these things, we have to ensure that this bandwidth doesn't cross this limit 10 by 10. So this is the relation between different bandwidths. B omega omega is basically FBWI by 10. So these are the design limitations which we have to understand. So why this 10 factor is coming and why other things are coming, we can see in the subsequent lectures. So these come basically from the power electronics requirement. So this is nothing to do with control. Only thing, we are maintaining the inner control loop faster, 10 times faster than the outer control loop. This is the control requirement. But why this limitation is coming, that is purely coming from the power electronics side. So we will see subsequently in the other lectures how it is done. Now today we have completed our control design or the control loop design for our system. So three parts which we discussed earlier: the power electronics, then our load, and then our controller. So for the separately excited DC motor, these two parts we have completed. Now the only thing remaining is how to design this power converter for this system. So far we have assumed the power converter as some gain Ka. So if you give any reference, V reference, the output is V, where output and input are related like this. But how do we achieve this? How do we achieve a good constant Ka gain, which is linear as well? So how do we achieve that? This is what we will discuss during our DC-DC power converter design. Now this can be discussed in the next class. So the floor is open. If you have some doubts in the controller design, you may ask now, or again we will have opportunity in the Tuesday's session. So then also you may ask.